Your objective for Lesson 17 is I will identify patterns in multiplication facts using the multiplication table. So we're going to be looking at a multiplication table today, and we're going to look for patterns to help us solve multiplication facts. So for this one, you are going to go ahead and need your problem set ready because we're going to be working through parts of your problem set whenever we are on the concept development. So if you need to push pause and have your problem set ready, you can do that now. Okay, you're going to need, you still need your whiteboard, but you will also need an orange crayon whenever we're working on your problem set. So if you need to push pause again, you can do that to get your orange crayon ready. Okay, write the products to complete the table in problem 1 and then color all the squares that have even products orange. So what you're going to do right now is you're going to complete all of the problems, all the multiplication equations that it has, and then once you have answered all of them, you're going to look for the products that are even and you're going to color those orange. So if there was a product that was 8, 2 times 4 is 8. So you would color that square orange because 8 is an even number. Now if you get to an equation like 3 times 3, that answer is 9 and that's not an even number, so you're not going to color that orange at all, you're just going to leave it blank. So your job right now is to answer all of the equations and then color the squares that have even products orange. So you need to push pause to do that. Okay, if you look up here on the page, this is what your problem set should look like whenever you completed all of the equations. And then you can see what you should have colored orange. All of the numbers that are not orange are odd numbers. So go ahead and push pause and double check that you have yours correct and push play whenever you're ready to move on. Okay, let's look at the first orange square in the table. So we are looking right here at 2 times 1 and it is equal to 2. I want you to write 2 times 1 on your board. And then I want you to ask yourself, are the factors 2 and 1 odd or even? So 2 and 1, are those factors odd or are they even? Okay, well 2 is even, but 1 is odd. So it is equal to 2. So even though I multiplied an even number and an odd number, it still equaled an even number. So I want you to remember that. In that equation, we multiplied an even number and an odd number, but it still equaled an odd number. Okay, look at the orange square below this one, which is 2 times 2 equals 4. Write that multiplication equation on your board, and then I want you to ask yourself, are the factors 2 and 2 odd or even? Well, 2 is an even number, and 2 is an even number, so that tells me right there that whenever I multiply 2 even numbers, it's going to be equal to an even number. So we've learned so far that when you multiply an even number and an odd number, that it is going to give you an even answer. And when you multiply an even number and an even number, it's going to give you an even answer. Okay, still looking at this chart, what did you notice about the factors of the even products? So look at all of the even products, meaning you're looking at the ones that are shaded orange. What do you notice about those factors? We just looked at this on the previous page as well, and we related the factors, seeing if they were even or odd. So we noticed that even times even is going to equal even, and odd times even equals even. So I want you to keep this in mind because whenever you're working on your multiplication facts, you can use this pattern to help you check your answer. Because if you're working with bigger numbers, say for example, you're working with 9 times 8. 9 is an odd number, but 8 is an even number. And we just learned that when we multiply an odd number and an even number together, it must equal an even number. So if you did 9 times 8 and your answer was 75, you know that that's not going to be right because 75 is not an even number, it's an odd number. So this pattern can help you check your answers whenever you're working on your multiplication facts and your multiplication equations. Okay, looking back at the table, find out what kinds of factors are required to produce an odd product. So we're not going to be looking at any of the orange squares. We're going to be looking at all of the white squares because all of those have odd products. So look at the numbers that they are multiplying to get that product. So let's take a look at 1 and 1. Is 1 an odd number or an even number? It's an odd number. So what they did right here is they took odd times odd, and it equaled an odd number. So let's go over here and check 3 times 1 and see if that still is true for this. 3 times 1 is 3. So is 3 an odd number or an even number? It's an odd number, and we know that 1 is an odd number as well, and it is equal to an odd number. So this tells me right here that you are going to get odd answers whenever you multiply if you're multiplying two odd numbers. So odd times odd is going to equal odd. So this is another pattern that can help you as well. Anytime you multiply two odd numbers, the answer must be odd as well. So going back to your problem set, I want you to go ahead and answer problem 1A and answer problem 1B. And I want you to push pause to do that. Whenever you're ready to check your answers, you may push play. Okay, so 1A says color all the squares with even products orange. We already did that. So the question says, can an even product ever have an odd factor? So product, remember, that is the answer. So if I'm looking at a multiplication equation, let's say blank times blank equals 9. Or let's say blank times blank equals, I'm thinking of, okay, 15, because that is an odd number. Or, sorry, it says, can it have an even product? So the product I'm looking for is 18. Okay, so you have to ask yourself, to get 18, what do I multiply? So you could do 6 multiplied by 3. Is 6 odd or even? It's an even number. Is 3 odd or even? It's an odd number. So this question says, can an even product, which is 18, ever have an odd factor? Well, we noticed right here that we multiplied 6 and 3 is an odd factor. So that tells me right there that yes, because odd times even equals even. You didn't have to explain how you knew that. It didn't say to, but I do want you to go ahead and write this on your problem set. Odd times even equals even, because that's just going to help you remember that whenever you multiply an even and an odd number together, we're going to get an even answer. You need to push pause to write that. You can do that. B says, can an odd product ever have an even factor? So that means that if I have the equation blank times blank is equal to 9, because 9 is an odd number. So remember back to what we just learned. Anytime we have an odd product, that's because the numbers that we multiplied together were odd numbers. So you can never get an answer in a multiplication equation that's an odd answer and have an even factor. So this right here is no, because odd products only happen with two odd factors. Or you could have put no, because odd times odd is equal to odd. You can never have an even number in your multiplication equation and then it be equal to an odd product. You will answer part C and D in just a second, but I want you to look back up at the chart and I want you to compare the shaded columns and the shaded rows. So remember, columns go up and down, so I've got shaded right here, 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 and here. And then my rows are going across, so here's a row, here's a row, here's a row, and here's a row. Which factors do they have in common in these columns and in these rows? I want you to push pause to try to figure that out. Okay, the factors that they have in common are 2, 4, 6, and 8. So you're going to look at problem 1C on your problem set now, and you are going to complete that. Whenever I scroll through here and find 1C, the question says, everyone knows that 7 times 4 is equal to 5 times 4 plus 2 times 4. So they used the distributive property and they broke 7 times 4 into 5 times 4 and 2 times 4 because 5 and 2 make 7. It says, explain how this is shown in the table. What that means is, how can you use this table to help you solve that whenever we're really looking at 5 times 4 and 2 times 4? So how can you use this table to help you solve that? That's how you're going to answer part C. So push pause to do that, and when you're ready to check your answer, you can push play. So the table shows 5 times 4 is 20, and it also shows 2 times 4 is 8. So all we have to do now is take the 20 and add the 8 to it, so it will give us 28. So that way we know 7 times 4 is equal to 28. Okay, going back to the concept development before you answer D. Is the product of 7 and 16 on this table anywhere? Do you see 7 times 16? When you look on here, no, you don't see that. It only goes to 7 times 8. So it doesn't go any larger than that. So how can we use this table and what we know to solve 7 times 16? So you're going to be looking at it just like they did in part C, where they broke apart a number. And in this case, what number are you going to have to break apart to help you solve this? You're going to have to break apart the larger number, so we're going to have to break apart the 16. So it's going to be 7 times something and 7 times something. So how can you use this table to help you solve 7 times 16 whenever we're breaking apart the 16? I want you to find 2 facts on this table that will help you solve 7 times 16, and I want you to write those 2 facts on your board. If it were me, I would have found 7 times 8 and add that product to the product of 7 times 8, because you could have broke your 16 into 8 and 8. So when I'm looking over here, I see that 7 times 8 is 56. So if I take 56 plus 56, it will give me 112. So that tells me that 7 times 16 is 112. So you can use this table to help you figure that out. So now you can go ahead and answer 1D on your problem set. Push play whenever you're ready to check your answer. Okay, so we're going to use what we know to find the product of 7 times 16, or we could say we have 8 sevens and 8 sevens. So this is what we just did. So you were to write how you would have used the table. So we could have broken apart 7 times 16 into 7 times 8 and 7 times 8, like it is on the table, and then we could have added 56 together, and it would have equaled 112. Okay, going back to the concept development before we move on in the problem set. Complete the chart in problem 2 by writing the products for each equation. So when you're looking at problem 2, you're only going to write the answers to 1 times 1, 2 times 2, 3 times 3, 4 times 4, 5 times 5, and 6 times 6. So on your problem set, I want you to write the answer in those squares to those equations. Push play whenever you're ready to check it. So we know that 1 times 1 is 1. We know that 2 times 2 is 4. We know that 3 times 3 is 9. 4 times 4 is 16. 5 times 5 is 25. And 6 times 6 is 36. So when we go back to the problem or the concept development, it says to look at the chart, and if it continued, what would the next equation be? So we went 1 times 1, 2 times 2, 3 times 3, 4 times 4, 5 times 5, 6 times 6. So you can kind of see the pattern that we're taking. So what would the next equation be if we were to continue going in that table? I want you to write that equation on your board. The next equation would be 7 times 7, and it would be equal to 49. So what would the next equation be if we were to keep going? Write that problem on your board. So the next equation would be 8 times 8 is 64. Okay, now we're going to work on part B of problem 2 on your problem set. You have to draw arrays to match each of these equations, and then you're going to record the change in the number of squares from one array to the next, and then you're going to figure out what is the pattern in the number of squares being added. So let's look at that problem on the problem set together. So they've already did 1 times 1 for you. If you were drawing an array for that, it would just be 1 square in 1 row. And now 2 times 2 would be 2 rows with 2 in each row. And you notice right here that from this to this right here, the difference in the number of squares is 3. They had 1 right here, and to go here, they added 3 more squares to get there. So we're going to continue drawing arrays for each one of these, and you're going to see how many more squares did they add to each one whenever we drew a new array. So I want you to draw arrays for 3 times 3, 4 times 4, 5 times 5, and 6 times 6. And then we will complete the numbers at the bottom to see how many squares they added to each array. So pause to do this. So when you're looking at 3 times 3, you've got 3 rows with 3 in each row. Here I had 4 squares total. Now I have 9 squares total. So I had to add 5 to this array to make this array. So right here on your problem set, you need to write the number 5. 4 times 4 is 4 rows with 4 in each row. So if I had 9 squares here, now I have 16 squares here. To go from 9 to 16, I had to add 7 more squares. So 7 goes right here on your problem set. 5 times 5, there are 5 rows with 5 in each row. I had 16 squares here, and now I have 25 squares here. So to go from 16 to 25, I had to add 9 more squares. And then right here, 6 times 6, I've got 6 rows with 6 in each row. And to go from 25 squares to 36 squares, I had to add 11 more squares. So what do you notice about these numbers down here at the bottom? 3, 5, 7, 9, and 11. What do you notice about those numbers and that pattern? You should have noticed that each one of these numbers is an odd number, so each time you're adding an odd number of squares to the array. This next pattern I want you to look at is pretty neat, and it's a cool way to find the answers to your doubles. I want you to look at 2 times 2, and this is only going to work with our doubles, so I want you to write down, and you can write it on your problem set, it's fine. Write down the first 2 odd numbers right above this problem. So I've got 1 and I've got 3. So if I add 1 and 3 together, what does that equal? And you're going to write that right over here next to it. So 1 plus 3 is equal to 4. So is 2 times 2 4? Well, the answer is yes. So far we know if we've got our doubles, all you have to do is actually tell, depending on what you're multiplying by. Since we were multiplying by 2, all you had to do was add the first 2 odd numbers, and that gave you your answer. So let's look at 3 times 3 and see if it still works. So write down the first 3 odd numbers. So we've got 1 plus 3 plus 5. And we're going to add that up, and we're going to see if it equals what 3 times 3 equals. So whenever I add 1 and 3, I get 4, and whenever I add 4 and 5, I get 9, and 3 times 3 also equals 9. So let's try this with 4 times 4. Write down the first 4 odd numbers. So 1 plus 3 plus 5 plus 7. And since 4 times 4 is equal to 16, we're going to see if 1 plus 3 plus 5 plus 7 is equal to 16. I'm not going to start with 1 plus 3. I'm going to start with making a 10. And I know that 3 and 7 make 10. So now I've got 10 plus 1 plus 5. And I can add that together a lot easier than starting with 1 plus 3. So I know 10 plus 5 is 15, and if I add 1 to that, it's 16. So those first 4 odd numbers added together equals 16, and so does 4 times 4. So let's go over here and try it with 5 times 5. If you write down the first 5 odd numbers, is it going to equal the same thing that 5 times 5 equals? I want you to try that out and see if this pattern continues to work for 5 times 5. Push pause whenever you're doing that. So the first 5 odd numbers are 1, 3, 5, 7, 9. So if we are adding these together, I'm going to start easy again. 3 and 7 make 10, and also 1 and 9 make 10. So I've got 2 10s right here that I'm looking at, and I know that 2 10s makes 20. And then I've got this 5 left, so if I add this 5 to 20, that is equal to 25, and so is 5 times 5. So this is a pretty neat pattern to help you work with your doubles. All you have to do is whatever your number that you're multiplying, that's how many odd numbers you have to write down. Add all of those odd numbers up, and that gives you your answer to your double. So if you didn't know 8 times 8, you could write down the first 8 odd numbers, add them together, and it's going to give you your answer to what 8 times 8 is equal to. So that's a pretty neat pattern to help you whenever you're multiplying with your doubles. Okay, we're going to move on to part C of the problem set. What pattern do you notice in the number of squares that are added to each new array? And we kind of just went over that when we looked at 3, 5, 7, 9, and 11. What pattern did we notice with all of those numbers? I want you to go ahead and write that down right here on your problem set and push play when you're ready to check it. When we looked at it, we noticed that the pattern was skip counting by odd numbers, or you could have put that we noticed that each number was an odd number. Either one of these would have been fine for this answer. So looking at D, use the pattern you discovered in part B to prove that 9 times 9 is the sum of the first 9 odd numbers. So this is a double. This is where we have to take the first 9 odd numbers and add those together. So for this problem, you're going to add the first 9 odd numbers and see if that is equal to what 9 times 9 is equal to. And I want you to push pause to do this. Okay, I want you to look at how I solved this. I wrote down the first 9 odd numbers, 1, 3, 5, 7, 9, 11, 13, 15, and 7. But I want you to look at how I took those numbers and combine some numbers to solve it easier. So I put 1 and 9 together to make 10. I put 7 and 3 together to make 10, and that's what I did previously. I put the 5 with the 15 to make 20, and then I put the 13 and the 17 together to make 30, and then left over I have 11. So when I have 10, 10, 20, and 30, that's the same as 10, 20, and then 20 and 20 make 40. And then if I have 40 and 30, that makes 70. And then I've got this 11 left over, so all I had to do was 70 plus 11, and it's equal to 81. So the answer to 9 times 9 is 81. You did not have to solve it like I did by making easier numbers, but I did want you to see how that is a good way to solve problems like this. Combine numbers that you know will make tens, and that will help you solve it quicker and easier. Okay, going on to the exit slip. Use what you know to find the product of 8 times 12, or it could be 8 sixes and 8 sixes. So this one right here is pretty much like you using the distributive property. You're just breaking apart 8 times 12. And then on number 2, Lewis says 3 times 233 is 626. Use what you learned about odd times odd to prove that Lewis is wrong. Whenever you're finished with this, I want you to bring me your exit slip so we can go over it.